Okay, I'm going to show you the codes we were supposed to see during the class, but it's going to be easier if I explain them to you asynchronously. That means not in real time. Okay, so let's go to the first one here. Here we have some filter coefficients. This variable called h1, which consists of just ones from 1 to 5, and this one here that consists of ones from 1 to 14. And then we will declare our horizontal axis that goes from 0 to pi, every pi divided by 255 samples, right? This is in radians per sample. Now we compute the frequency response of both filters here, and then we calculate both filters' magnitude response, and well, we plot their magnitude response, and then we will plot their phase response. Remember that some filters change the phase every depending on the filter order, right? So let's run the code, and here we can see the resulting graph. Just give me a minute. Okay, let's see the resulting graph. So in this case, we have the magnitude response of both filters. The one with higher order presents less over impulses here on the filtered part of the signal. And these are the phase response for each filter. The one with less coefficients presents less changes in phase compared to the one with 5 coefficients, which has a lot of changes in its phase, right? So the more coefficients we have, the more efficient the filter will be. Now let's take a look at a Butterworth filter. We saw the Butterworth filter from the analog point of view. We are now going to see it working here in Matlab. It is declared with this function here, butter. So basically, whenever we want to filter a signal, we need to declare the filter first and then filter it using this function here. In this function, we filter the input signal with whatever filter we declared here first. Okay, so we have an input signal, which is an audio file of a guitar tune. We had a cutoff frequency of 800 hertz. We then declare the Butterworth filter. Then we use this function to get the filter frequency response, the magnitude response of the filter. And here we finally filter the signal, which will be stored. In B, we will store the filter design with its cutoff frequency. So we declare the filter and the cutoff frequency and the signal we want to filter. And finally, we get the resulting signal, which is going to be um, named as filtered signal right here. This is the input signal, the cutoff frequency, and the filter. And we will save the filter signal, the filtered signal as yesFilt.wave, and the no filtered signal, it's going to be named nofilt.wav, right? So we will run the code. We will see the magnitude response first here. This is the magnitude response. This is the phase response of the filter. As you can see, it is a higher order filter because we don't have many changes in phase. And we are going to listen to the resulting files here. So here we have filtered, the unfiltered version first. Let's open it using Windows Media Player. Okay, this is the unfiltered version of it. Okay, now we're going to listen to the filtered version of it. So here we are. It's much more darker than the other one. Okay, and we are going to take a look at one last example using a finite impulse response filter, which is going to be declared here using this Matlab function, where we need to declare the cutoff frequency in radians per sample and the filter order here. Remember, the bigger the order, the better the filter. In analog domain, this can be quite tricky, but on the digital domain, we just change the numbers here. So we first load the audio file and store it into a variable called A1, and then we will save it as a file, as a WAV file called A1, okay? And then we will use this filter here, which is going to be stored on variable B, and we again use the filter function we used when I showed you the Butterworth filter, and we are going to filter the input signal here. We want to see also the magnitude response, and we want to see it graphically. And after that, we will use the filtered version also to save it into a WAV file so we can listen to it afterwards. And well, here we sound both versions, but they will sound very, I mean, they won't sound good because they will be stopping because of the processing time. That's why I prefer to save them and listen to them later.